Welcome back, my students. Dr. Ogwe here. Today I bring you learning objective number 2 from cardiac action potentials, which is chapter 31 from uyton. And today we are going to study cardiac muscle action potentials. No need to write anything. My handwritten notes are in the description of the lecture. Go check them out. So we are studying cardiac muscle action potentials. We have two types of muscles in heart. We have the atrial muscle and ventricular muscle. The action potential in both of these muscles is similar. So if we study ventricular muscle action potential, it is equal to atrial muscle action potential. So we call it cardiac muscle action potential. So if we study one of these, we study all of these. Clear? So we are studying ventricular action potentials or cardiac muscle action potentials. They are one and the same thing. These cardiac muscle action potentials have 5 phases: 1, 2, 3, 4, and 5. And we will see these one by one along with their graphical representation. Now let us suppose this we have is a ventricular muscle cell. This right here is a ventricular muscle cell, and this is the membrane of the ventricular muscle cell. Now the voltage changes across these membrane. If we put one electrode inside of the membrane and one electrode outside of the membrane, and then measure the voltage changes across this ventricular membrane, these voltage changes are action potentials. Since this is the membrane of the ventricular muscle cell, so they are ventricular action potentials. Is that clear? Now, when we put an electrode inside of this ventricular muscle cell, we find that there is a lot of negative ions inside the cell. Because of that, there is negative charge inside. When we put an electrode inside of the cell, we found out that there are a lot of negative ions inside of the cell, inside of the fiber. So the inside of the fiber is negatively charged. And when we measured that charge on an electrode, we found that that charge is equal to minus 90 millivolt on an electrode. Is that clear? So the voltage inside of the cell is minus 90 millivolt. This cell right now is resting. This cell right now is resting. That means we have not given any external stimulus to a cell. We have not disturbed the cell. This cell is resting. Clear? And when we measured this potential in a resting stage, we found that this potential in a resting stage is minus 90 millivolt. So we call this minus 90 millivolt as a resting membrane potential. Because the voltage inside of the cell which is resting, is equal to minus 90 millivolt. So this minus 90 millivolt is called membrane potential in a resting stage. That's why RMP in a resting stage, that's why RMP is minus 90 millivolt. Now, when we give a stimulus to a cell, when we give stimulus to this ventricular muscle cell, this is a stimulus. Till now, the cell was not disturbed. When we give a stimulus to the cell, there is the entry of a lot of positive charge. That positive charge can be sodium, that positive charge can be calcium. Now this calcium and sodium, this positive charge neutralizes these negative ions. When they neutralize these negative ions, they take this resting membrane potential to minus 80 millivolt, then to minus 50 then to minus 60 millivolt, then minus 50, then minus 20 millivolt. Because of the entry of these positive charge, what happens is these positive charge neutralize these negative charge, and they take this voltage from minus 90 to minus 80, then minus 70. Is that clear? Now I will show you this in a graphical representation. This activity will be shown on a graphical representation. Let us suppose this is x-axis, and on x-axis we have time. Clear? And on y-axis we have voltage in millivolts. Initially the membrane was at minus 90 millivolt. That was resting membrane potential. The membrane was at rest. We had not disturbed the membrane, and when we measured the potential inside, that was minus 90 millivolt, and we called it resting membrane potential. Now when we give this stimulus, some positive ions, sodium and calcium, came with the stimulus, and they neutralizes this negative, and they took the voltage from minus 90 to minus 80, then minus 70. So this voltage, which was at minus 90 millivolt, got towards a lesser negative value, towards minus 80, then minus 70 millivolt. Clear? Now an important point: more the strength of stimulus, more will be the influx of this positive charge, and more will be the neutralization of this negative. Clear? So more positive charge coming inside, more will be the neutralization. Clear? Now a strange thing happens at minus 70 millivolts. when the membrane potential comes from minus 90 to minus 80, then to minus 70 millivolt because of the entry of the sodium and calcium. Now at this minus 70 millivolt, a strange thing happens. So now the membrane potential is minus 70 millivolts. This membrane senses that inside the potential is minus 70 millivolts. When the membrane senses this minus 70 millivolt, there is opening of lot of channels. There is opening of lot of channels, and these channels are voltage gated sodium channels. And when they open, there is lot of sodium influx. There is lot of sodium influx that come inside the cell. Clear? So at this minus 70 millivolt, there is opening of lot of voltage gated sodium channels, and lot of sodium comes inside the cell, and lot of sodium comes inside of the cell, and this sodium neutralize these negative ions, and they take the potential from minus 70 to minus 60, then minus 30 up to plus 20 millivolt. Clear? So at minus 70 millivolt, a lot of voltage gated sodium channels open, and they take the potential. With time is increasing, with time the voltage got from minus 70 then minus 60 up to plus 20 millivolt. Clear? It occurs because of the entry of the sodium through voltage gated sodium channels. Is that clear? Now this minus 70 millivolt, it's an important voltage. Why it is an important voltage? We call this firing level. We call this firing level or threshold level. Threshold level. Why we call it firing level or threshold level? Because at this minus 70 millivolt, voltage gated sodium channels open. So this minus 70 millivolt is a threshold. Before that, at minus 75 or minus 80 or minus 90, these voltage gated sodium channels do not open. They are closed. They get open, they get sensed at minus 70 millivolt. So these are voltage gated. They sense the voltage. They sense this voltage minus 70 millivolt. So this voltage is known as firing level or threshold level. Is that clear? Now the voltage, now the graph goes from minus 70 to plus 20 millivolts with time. Time is increasing. Clear? And this phase from minus 90 millivolt to plus 20 millivolt is called phase zero. Phase zero of action potential, or it is also known as depolarization phase. Depolarization phase, and it occurs because of sodium influx. Is that clear? Now when the membrane potential is plus 20 millivolt. Clear? Now the membrane senses, this ventricular membrane, it senses that the inside potential is plus 20 millivolt. When it senses the inside potential when the membrane senses that inside potential is plus 20 millivolt, it closes these sodium channels and it opens a different set of channels. These channels are potassium channels, and through these channels potassium go out. And when the potassium is going out, that means positive charge is leaving the cell. This plus 20 millivolt goes to minus plus 10 millivolt, then 0 millivolt, then minus 10 millivolt. So due to the exit of the potassium, this positive potential goes towards a negative value. Is that clear? So what happens is that at plus 20 millivolt, potassium channels open and these sodium channels close. These potassium channels are open. They take the potential, let's suppose, from plus 20 to plus 10 millivolt. Is that clear? And this phase is known as phase first or initial repolarization. Initial repolarization phase, and it occurs because of closure of sodium channels and potassium exit. Is that clear? Now at plus 10 millivolts, another set of channels open. Now the potential got from plus 20 to plus 10 millivolts. Now when the potential is plus 10 millivolts, this membrane senses this, and there is opening of another type of channels, and these channels are calcium L type of channels. And what happens through these channels? Calcium comes inside. But there is a peculiar thing, there is a strange thing happening. This entry of calcium is equal to the exit of this potassium. These channels are not stopped yet, they are not closed yet. So the potassium is exiting the cell, but there is an opening of another set of channels. Those are calcium L type of channels. But this calcium entry is equal to the potassium exit through these channels. So what happens in this phase? The potassium that is going out of the cell, the charge that is equal to the calcium that is coming inside the cell. As a result, this potential doesn't change, it remains at a straight line, because the amount of the amount of potassium that is going out of the cell is equal to the amount of calcium that's coming inside of the cell. That is, the charge leaving the cell is equal to charge coming inside of the cell. Is that clear? And this phase is called phase 2 or plateau phase. Plateau means a straight line. It is because of the equal amounts of potassium efflux and calcium influx. Is that clear? So the graph remains stationary. Now after some time, these calcium L type of channels close. And there is only potassium exit. So after some time, these calcium L type of channels close and only these potassium channels remain functional, and potassium is going out of the cell. When the potassium is leaving out of the cell, they take the potential from plus 10 millivolt to back to minus 90 millivolt. Is that clear? So now this calcium channel is closed, there is this potassium efflux continued, and they take the potential from plus 10 millivolt back to minus 90 millivolt. Is that clear? And this phase is known as phase 3 or late repolarization phase. It is because of this continued potassium exit. So in initial repolarization, potassium is exiting. In phase 2 plateau phase, potassium is exiting. In phase 3, potassium is exiting. So in these three phases, potassium is continuously exiting. Only one thing happens in middle, that is calcium influx, which matches potassium influx. Clear? There is calcium influx which matches potassium efflux. Is that clear? In the plateau phase. So the amount of calcium that's coming inside is equal to the potassium that's leaving the cell in the plateau phase. And after some times, these calcium channels close and this potassium efflux is continued. So this is the phase 3. So this phase 0, this phase 1, this phase 2, this phase 3. Now the last phase that occurs is at minus 90 millivolt. It is called a resting membrane potential. So this is the phase 4 or resting membrane potential maintenance. What happens in this resting membrane potential maintenance? During the course of the action potential, you saw that this sodium is coming inside of the cell. So the sodium accumulates in the cell, and this potassium is going out of the cell, and this potassium is accumulating outside of the cell. Now during this maintenance of resting membrane potential, this sodium is taken outside of the cell, and this potassium is taken back inside of the cell by a motor, by a ATPase motor. That's called a sodium potassium ATPase motor. So what does it do? Sodium potassium ATPase motor, it maintains this minus 90 millivolt resting membrane potential. It maintains this value and takes potassium inside of the cell and sodium out of the cell to maintain the ions, to maintain the ion balance. Clear? So the sodium that came inside during the course of action potential and the potassium that got out of the cell during the action potential, they are reversed by these sodium potassium ATPase motor. Is that clear? These are the 5 phases of cardiac muscle action potential. Now some points. First we will revise it. Depolarization occurs because of the sodium influx. Initial repolarization occurs because of the potassium efflux. Plateau phase occurs and because of the equal amounts of calcium influx and potassium efflux. Late repolarization occurs because of the potassium efflux, and resting membrane potential occurs because of the sodium potassium motor. These are the 5 phases of action potential. Now an important thing, why this phase 0 is called a depolarization phase. Look here, inside the resting membrane potential was negative 90. So inside the potential was negative. At the end of depolarization, the potential is now positive. So first initially it was minus 90 millivolt, now it is plus 20 millivolt. So the negative became positive. So there is loss of polarity in the membrane. That's why this phase 0 is called a depolarization. That means loss of polarity. While as in initial repolarization and late repolarization, membrane potential is taken back from plus 20 to minus 90. Is that clear? In initial repolarization, there is an attempt to take this potential back. But in late repolarization, this potential goes back from plus 10 to minus 90, from positive to a negative value. So that's why it is called repolarization phase, meaning regaining of polarity, regain that initial minus 90, that's regaining of our charge, regaining of initial charge. Clear? Now, why doesn't the potential, sometimes if this potassium efflux remains remains excess. So if this potassium efflux remains continue, it can take the potential from minus 90 to minus 100. minus 100 millivolt or minus 110 millivolt, that stage is called hyperpolarization stage. That means extra polarity. Clear? Hyperpolarization means extra polarity. Is that clear? Now, two important points, and with that we will close our topic. This phase right here is called plateau phase. Clear? What happens in this plateau phase? There is calcium influx and equal potassium efflux. This calcium which is coming inside of the cell, this calcium is responsible for ventricular muscle cell contraction. Clear? We all know that from previous lectures that calcium is responsible for muscle contraction. And where this calcium comes from? It comes from calcium during the plateau phase. We know that this right here is a ventricular muscle cell. Clear? This calcium, where does this calcium comes from? L type of channel, it comes from extracellular fluid. So calcium is coming from extracellularly. So this calcium comes from extracellular fluid, and this calcium is responsible for this contraction of the cell. And how does this calcium cause contraction of a cell? We have studied it in properties, physiological properties of cardiac muscle. Clear? So in a cardiac muscle, calcium comes from extracellular fluid. This is something that does not happen in skeletal muscle cell. Let us suppose this is a skeletal muscle cell. Clear? Skeletal muscle cell also requires calcium for its contraction, but it does not come from extracellular fluid. It comes from inside. Where does it come from? It comes from sarcoplasmic reticulum. So in skeletal muscle cell, the calcium that is required for contraction comes from intracellular, that is sarcoplasmic reticulum, while as in ventricular muscle cell, the calcium that causes contraction comes from extracellular fluid, while as in ventricular muscle cell, the calcium that causes contraction comes from extracellular fluid, and a small amount of calcium also comes from sarcoplasmic reticulum. This was an important question that came in NEET PG examination, that the calcium in ventricular muscle cell or a heart cell comes from extracellular fluid that you saw here in the plateau phase. This calcium L type of channels, but some amount of calcium comes from sarcoplasmic reticulum as well. While as in skeletal muscle cell, there is no extracellular calcium. All the calcium comes from sarcoplasmic reticulum. This was a question in NEET PG 2019. Clear? Now a last question. You saw this is the ventricular action potential. There was this phase, this straight phase, this is called plateau phase. An important point in this plateau phase is that this plateau phase, it causes cardiac muscle to contract 15 times more as compared to a skeletal muscle. That means if skeletal muscle contracts for 1 second, this cardiac muscle will contract for 15 seconds because of the presence of this plateau phase, this straight line, this phase 2 of action potential, plateau phase. I have shown this in a diagrammatic representation. If you can see that here, this is the diagrammatic representation. This is a skeletal muscle. It is its action potential. This is the electric response, and it causes a contraction. Let's suppose this contraction is for 1 second, as you can see here. Clear? And here we have a cardiac muscle. This is the electric response, that is the action potential of the cardiac muscle, and this right here is its plateau phase. And due to this plateau phase, the contraction of it in a cardiac muscle lasts 15 times more. Here it was 1 second, here it will be 15 into 1, that is 15 seconds. So the contraction lasts 15 times more, 15 per 15 seconds. Clear? So the contraction in cardiac muscle is longer because of the presence of this plateau phase. It's an characteristic feature of this cardiac muscle. It is not found in the skeletal muscle because skeletal muscle contraction is very slower. Why is it slower? Because there is no plateau phase, as you can see in the electric response. But in the cardiac muscle, there is a plateau phase, and because of the presence of this plateau phase, contraction lasts 15 times more. Here the contraction was for 1 second, here the contraction is for 15 seconds. It is an important characteristic feature in a cardiac muscle. Now one last point that we will talk about. Clear? One last point is that this right here is an action potential of a cardiac muscle cell. Clear? This right here is an action potential of a cardiac ventricular muscle cell, and this right here is a depolarization. This depolarization occurs because of the sodium influx. But in the previous video, we told you that this part is the depolarization of a SC node. This depolarization occurs because of the calcium influx through L type of calcium channels. Clear? So in SA node, depolarization is because of L type of calcium channels through calcium, while as in ventricular muscle cell, depolarization is because of sodium. Clear? This is a difference between the action potentials between SA node and ventricular muscle fiber. But this calcium is an important thing. The depolarization in SA node due to this calcium is unique to SA node. I will write it down. So SA node depolarization is because of calcium. Clear? And depolarization is ventricular muscle cell occurs because of sodium. Clear? Everywhere you see depolarization occurs because of sodium except in SA node. This calcium depolarization is unique to SA node. It's a unique property of SA node. So with that I'm concluding our topic today. That's depolarization, that is action potential in a ventricular muscle cell. Do check my notes out. Clear? In my Telegram channel in my description. And a student told me that in the previous video that what kind of pens you use. These are the pens, LUXOR or T, I guess. You can get these pens in anywhere, Flipkart, Amazon. Do subscribe my channel. Thank you very much. Your Dr. Ogwe. Class dismissed.